In this screencast, we're going to look at eigenvalues and eigenvectors. The idea behind eigenvalues and eigenvectors is when can you replace matrix multiplication by scalar multiplication? An example of this, let's just take a matrix 2, 1, 1, 2, and let's multiply it by the vector 1, 1. Well, that's the same thing as taking 2, 1 times 1 plus 1, 2 times 1, which yields, put it in here, 3, 3. Well, that is the exact same thing as 1, 1 times 3. Notice that I took the matrix and replaced it with scalar, and so I'm just replacing matrix multiplication with scalar multiplication. This won't happen for every pair of vectors and scalars. Let's just look at another example. If I take 2, 1, 1, 2 and multiply it by something like 3, 1, then out pops 2, 1 times 3 plus 1, 2 times 1. And that is the same thing as 6 plus 1, which is 7, and 3 plus 2, which is 5. Well, that is not 3, 1 times some scalar. So this is not an eigenvector, and there's no eigenvalue that'll turn this into an eigenvector. This number is called an eigenvalue. This number is called an eigenvector. So the idea is, when can you take a matrix and multiply it by a vector and get a scalar times the vector? Now, jump down and we'll look at this in general. If we take an ax equals lambda x, how do we find the lambdas and the x's such that things like that, what happened above, hold? Well, I can rewrite this as ax minus lambda x equals 0. And it would be great if I could factor an x out. I could if they were both matrices, but a and lambda, that's a matrix, that's a scalar. So we're going to insert the identity matrix in the middle, and that allows us to write a minus lambda x is equal to a minus lambda I times x is 0. Well, here I have a matrix, a minus lambda I times a vector being 0. Well, the only way I can do that is if I take a linear combination of the columns of B and get 0. Well, a simple way to do that is if x is 0. Then, well, if x is 0, you could put a 0 here and a 0 here, and lambda could be anything. So we're going to make a stipulation that x is not 0. So the only way this can be true is if there is a linear combination of the columns, which gives me 0, which means that the columns of B, or the determinant of B, is 0, and the columns of B are linearly dependent. So what we're going to do is we're going to find the determinant of a minus lambda I, and we'll ask, when is that 0? So we're going to compute that. First, what in the world is a minus lambda I? Well, we take 2, 1, 1, 2, and a minus lambda times the identity matrix. Well, that gives me the same thing as 2 minus lambda, 1, 1, and 2 minus lambda. Notice I'm just subtracting lambda from the diagonals. Now I want to take the determinant. So the determinant of 2 minus lambda I, lambda 1, 1, 2 minus lambda is, there's a 2 minus lambda times a 2 minus lambda minus 1 times 1. So that is 4 minus 4 lambda plus lambda squared minus 1, which is lambda squared minus 4 lambda plus 3, which factors as lambda minus 3, lambda minus 1, which means 3 and 1 are our eigenvalues. These numbers right here are precisely the only possible eigenvalues. Notice the number 3 shows up down here. Well, if I have an eigenvalue, how do I find the eigenvector? The idea, if I want to find eigenvectors, is I want to solve that equation up there. I want to solve a minus lambda I times x is 0. Well, that really just means I need to take the matrix a minus lambda I, augment by 0, and then row reduce. Here is a minus lambda I. So if lambda is 3, then I can come up here and put in a 3. I get a negative 1, 1, 1. Negative 1 will augment by 0, and now I need to reduce. Notice if I just take row 2 plus row 1, the bottom row will cancel, so I have a negative 1, 1, 0, 0, 0, 0, and then I could multiply the top row by negative 2, finish putting it in reduced to echelon form. Well, this top row tells me that x minus y is 0. This bottom row, well, there was no pivot in the second column, so y is a free variable, which means x is y and y is y, or in vector form, that's y times 1, 1. All of our eigenvectors are of the form y times 1, 1. So eigenvectors are linear combinations of 1, 1. And I'm going to make a point, they're non-zero linear combinations of the vector 1, 1. Notice here's our 1, 1, and that's where we got that from. We're now going to look at the next one. If lambda was 1, our other eigenvalue, then what does our matrix become? Well, we'll come back up here, we'll put in a 1. 2 minus 1 is 1. 1, 1, 1. Augment by 0, and if I reduce, that just becomes simply 1, 1, 0, 0, 0, 0. Well, this is the same thing as x plus y is 0, and y equals y. This top line turns into x equals minus y. Well, I can turn that into a vector by, I notice there's a negative y, so negative 1 and a positive y, 1, y. Here are our eigenvectors corresponding to lambda equals 1. The eigenvectors are, there's infinitely many of them. Notice I get an infinitely many here, linear combinations of that one. There's infinitely many here, linear combinations of negative 1, 1. And I get two different sets of eigenvectors to go with the two eigenvalues that I found. That completes this screencast.